Let's begin with the basic data types available in C programming language. C language has 4 basic data types. They are char, int, float and double. The char data type is 1 byte long, and can be used to save a character or 1 byte of data. Int data type is usually a word long, and can be used to save an integer value. Float can be used to save a single precision floating point value. And double can be used to save a double precision floating point value. On a 32-bit operating system, char is 1 byte long, int is 4 bytes, float is also 4 bytes and double is 8 bytes. The size of the basic data type can vary from platform to platform. Check your compiler documentation to know the size on your platform. The special keywords short and long can be used to vary the size of the above data types. For example, short int is just 2 bytes whereas long float is 8 bytes. Now that we know the size of each of the basic data types, let's see how are the variables of these data types allocated in memory. Consider a small program, which allocates few variables of different data types. The picture on the right side shows how these variables might get allocated in the memory. Each variable is given space in memory based on its data type. For example, the variable C is of the data type char, hence it's given 1 byte in memory, whereas the variable I is of the type int, hence it is given 4 bytes in the memory. Similarly for other variables, the memory is allocated based on its data type. Please note that the order of allocation of memory for variables can vary from platform to platform. Also, when the compiler is allocating space in memory for these variables, it might pad unused memory between some variables for alignment, as shown in the figure. This is mainly done for performance reasons. We would discuss memory padding in detail later in the course. Having looked at the way memory is allocated for a variable, let's see how the bytes of a data type is laid out in the memory. As we all know, there are both kind of languages, where people write from left to right and in some, they write from right to left. Same way, bytes inside a data type can be written from left to right or right to left. This is dictated by the NDNS of the processor. NDNS of the machine defines the ordering of the addressable units within a longer data type. An addressable unit is the minimum length of data that can be addressed inside a processor. The machine, which write from left to right, are called big-endian machine. The big end of the data is written first, hence it is called big-endian. Most of the PowerPC-based processors are big-endian machines. The machines, which write from right to left, are called little-endian machines. The Intel-based machines are little-endian. The little n is written first, hence it's named little-endian. In big-endian machines, the MSB of the data type is written first followed by the lower significant bytes. Whereas in the little-endian machine, the LSB is written first, followed by the higher significant bytes. We would see them in detail in the following slides. Let's look at an example to understand the NDNS better. For simplicity, let's first assume that the addressable unit for the processor is 1 byte. So if we declare an integer I, and if it's 4 bytes long, then the bytes within the integer data type can be allocated in 2 fashion. In big-endian machine, the byte 0, which is the most significant addressable unit, is placed first in the memory followed by the other lower-order addressable units. But if you look at the same integer in little-endian machine, the least significant addressable unit, which is byte 3, is placed first in the memory followed by the other higher significant addressable unit. As you can see, the representation of the same value or variable in both the machines are very different. You should know this, if you are doing debugging in assembly mode, and if you look at the raw data in the memory. Based on the architecture of the processor, you should interpret the content of the memory. Let's look at a real example. If we have an integer which is 4 byte long and it is initialized to a hexadecimal number given in the example at the bottom. In the big-endian machine, the most significant unit, which is the byte 0x12, will be placed in the memory first. In the next memory location, the next unit, which is 0x34, is placed, followed by the other units. If you observe, it looks like the processor is writing from left to right. But in little endian machine, the least significant unit, which is the byte 0x78, is placed first, followed by 0x56 in the next memory location. In this case, it looks like the processor wrote in the memory from right to left. Let's look at more examples to understand endianness better. Let's take the same integer and see how the integer will be laid out in memory in different processors with different addressable unit length. Let's first consider a machine with addressable unit of 2 bytes. In this machine, the units in a larger data type will be laid out 2 bytes at a time. It's like 2 byte is one entity for the processor. So, in big-endian machine, the most significant unit, that is 0x12, 34, will be placed in the memory, followed by the second unit, which is 0x56, 78. The same integer in a little endian machine will be saved in the reverse order, with each entity being 2 bytes long. The least significant unit, that is 0x56, 78, will be first saved in the memory, followed by 0x12, 34. Now let's try the same on a machine with the addressable unit of 4 bytes. In this case, the size of the data is equal to one addressable unit. And as we know, the ordering happens to the units within a data type. In this case, the ordering will not matter, because the data is just 1 unit long. So in both the machine, the memory layout of this variable will be same. For practice, try this on a 8 byte long data type.